In this video, I will walk you through some multiple choice questions from past AP exams that pertain to Unit 5, which is about Introduction to Integrals. For problem number 1, I have an integral set equal to 16. So I need to somehow solve this for k, which represents a constant. Let's go ahead and evaluate this integral term by term. So the integral of x to the 7th power, we use the power rule of integration. Increase the exponent by 1, you get 8. Divide by the new exponent, you have 1/8. And then if you integrate a constant, then you get an x. So I have kx. So the limits of integration are from -2 to +2. In order to evaluate this, I need to find the value at 2 and then subtract the value at -2. So here is the value at 2, and here's the value at -2, and all of this should equal 16. On this step, I put the 2 here in the front of the k, and I distributed the minus sign. So one other thing that happened, I have this -2 right here, but when I distributed the minus sign, a negative times a negative is a positive. So I have a positive 2k. Notice that these terms are actually the same, because if you raise a negative number to an even power, it actually becomes positive. So both of these yellow expressions have exactly the same value. And I'm subtracting them. So these are going to actually cancel each other out. So I am left with 2k plus 2k, which is 4k, equals 16, which means that k is equal to 4. So the answer is D. Number 2, evaluate the integral of the absolute value of x minus 1 from 0 to 3. By far, the easiest way to evaluate the integral of an absolute value is graphically. We know that the parent function for absolute value is a V shape that normally starts at the origin. So when you see the x minus 1, you just need to understand that the minus 1 is a transformation that will shift the v 1 unit to the right. So here is the portion of the absolute value graph that falls between 0 and 3. We know that the integral of a function from 0 to 3 is the area between the function and the x-axis from 0 to 3. In other words, the integral from 0 to 3 is the shaded area here. Because this area is above the x-axis, it will be considered positive. So we have two positive areas, and they're both triangles. So 1/2 base times height. If you take the small triangle, we have 1/2 1 times 1. And if you look at the larger triangle, 1/2 base times height is 1/2 2 times 2. But this first term is just 1/2. And 2 times 2 is 4. Half of 4 is 2. So in the end, we have 2.5. Well, I'm looking at my options, actually, because multiple choice, and I'm not seeing decimals. So let's leave this as a fraction. So I have 1/2, and let's make like denominators. So 2 is the same thing as 4 over 2, and adding these fractions, I get 5 over 2. So this is probably what I will see among the answer choices. And there it is, D. Number 3. If the integral of f of x from 1 to 10 is equal to 4, and the integral from 10 to 3 is equal to 7, then find the integral from 1 to 3. The limits of integration involve these three numbers. So we have 1 to 10, which is from here to here. We have 10 to 3. Interesting, that's backwards. We'll have to deal with that later. But anyway, from 10 to 3 is from here to here. And then we have from 1 to 3, which would be from here to here. The number line, that's a smile. The number line helps you sort of visualize the relationship between these three integrals. My strategy will be to make an equation out of these integrals that says the integral from 1 to 3 plus the integral from 3 to 10 is equal to the integral from 1 to 10. So basically we have part plus part is equal to the whole. Keep in mind that the integral from 1 to 3 is the one we are looking for. So as I solve this integral equation, I'm just going to start by bringing this straight down. Next, here comes a potential pitfall that I need you to watch out for. We need this integral right here to be the integral from 3 to 10 in order to complete this sort of chain that we have going. We've got 1 to 3, 3 to 10 is equal to 1 to 10. However, the integral that they gave us was backwards. They gave us the integral from 10 to 3, right? See how that's like big to small? That's weird. So we need to reverse this. Reversing the limits of integration will give you the opposite sign. So if the integral from 10 to 3 is equal to positive 7, then the integral from 3 to 10 will be negative 7. We can complete the equation like this because we were given that the integral from 1 to 10 is 4. In order to get the integral from 1 to 3 by itself, we will add 7 to both sides. So we have the integral of f of x from 1 to 3 is equal to 11. And that is E. Number 4, what are the values of k for which the integral of x squared from negative 3 to k is equal to 0? Let's just start evaluating this integral like we would if k were any other constant. Like if this was negative 3 to 5, what would we do? Well, the integral of x squared, we will use the power rule of integration. Increasing the exponent by 1, we have x to the third power. Now, dividing by this new exponent, we have 1/3. But we need to evaluate using the limits of integration, which are from negative 3 to k. And this should equal 0. But the way we evaluate is we find the value at the upper limit, and then we subtract the value at the lower limit. So we will do 1/3 times k to the third power, and then minus 1/3 times negative 3 to the third power. And that is supposed to equal 0. Simplifying this a little bit, I'm taking away the brackets. So 1/3 k to the third power. Negative 3 cubed is negative 27. So we have 1/3 times negative 27. And that's equal to 0. Well, a negative times a negative is a positive. K to the third power. So I'm going to have plus something. And 1/3 of 27 is 9. So we have this equation. Now we have a tiny bit of algebra. 1/3 k to the third power. Subtracting 9 from both sides, this will equal negative 9. Multiplying both sides by 3, we'll take out this 1/3. So we will have k to the third power is equal to negative 27. Next, we will take the cube root of both sides of this equation, and that will leave us with k is equal to -3. So that is the answer. So the answer is A. I thought it might be fun to solve this same problem a different way. Let's look at this problem graphically. We know that the integral of x squared from -3 to k is the area under the curve from -3 to k. So we want this net area to equal 0. However, all of this area is going to be positive because it is above the x-axis the entire time. So there is no negative area no matter where we put this k. So visualize this k as moving from left to right, and we're looking for where will k be that will cause the overall area to be 0. But right away you start off with a positive area, and then you just add on more and more and more area as k goes to the right. So where will you ever get 0? The only way to get 0 area is to let k equal -3. That way, we are now talking about the integral of x squared from -3 to -3. This will have a 0 area because there is no space between -3 and itself. So this is a way to figure out that the answer is A without necessarily doing any work. Number 5. If f is a continuous function and capital F prime of x equals f of x for all real numbers x, then the integral of f at 2x dx from 1 to 3 equals what? First of all, this little statement right here just means that capital F of x is an antiderivative of f of x. So later, when we evaluate the integral of f of x, we will call the result capital F of x. Because we see a function inside of this function, we need to use U-substitution to evaluate the integral. I'm going to show this in two ways. First, I'm going to do it by changing the limits of integration, and then I'll show you how to do it without changing the limits of integration. You can decide for yourself which way seems easier. So let's let u equal 2x, because that's what is inside the function. If u is equal to 2x, then that means u prime will equal 2. In order to change the limits of integration, we need to change these x values into values of u. Let's start with u at 1, and we're using this equation right here. So u at 1 will be 2 times 1, which is just 2. So when I rewrite this, instead of a 1, I'll put a 2. Similarly, u at 3, okay, I'm looking at this limit. So u at 3 will be 2 times 3, which is 6. So when I rewrite this, I'm going to put a 6 instead of a 3. So as we set up the U-substitution, it looks like this. The new limits of integration are from 2 to 6, and we now have f at u, and instead of dx, we will put du divided by u prime, which is 2. Since we are dividing by 2, I'm going to put this out front as a 1/2. Again, this statement right here is telling us to call the integral capital F. So that's what we are going to do. So when we take the integral, the f of u becomes capital F of u. And we still have the 1/2. And we need to evaluate using the limits of integration. So from 2 to 6. This means we need to find the value at 6 and then subtract the value at 2. So that will give us 1/2 capital F at 6 minus 1/2 capital F at 2. So we see that the answer is E. So that's how you would do it if you wanted to change the limits of integration. So here is another way to do it without changing the limits. We will end up keeping the 1 and the 3. For this method, first rewrite the definite integral as an indefinite integral. In other words, take away the limits of integration. So we have this. Now we will do our usual U-substitution. So let's let U equal 2x, and therefore U prime will equal 2. Here comes the substitution. So we have the integral of f at u, and instead of dx, we will write du divided by u prime. So instead of putting the 2 here like I sometimes do, I will immediately put it as 1/2 out in the front. We were told to call the integral capital F, so that's what we do. And we have 1/2 capital F of u plus c, because this was an indefinite integral. So now we will substitute 2x back in for u, and we will turn this back into a definite integral by including the limits of integration. So this will become 1/2 capital F at 2x, and we will evaluate using the limits of integration, the original limits of integration, from 1 to 3. So we will find the value at 3 minus the value at 1. So this will give us 1/2 capital F of 2 times 3, so that's the value at 3, minus 1/2 capital F of 2 times 1, the value at 1. But obviously, this is 1/2 f at 6 minus 1/2 f at 2, so we can see that the answer again is E. Let me emphasize one thing. If you use this method and you decide to keep the original limits of integration, it is very important that you drop these limits of integration when you do the U substitution and bring them back later after you put the x's back in. If you do this and you keep the 1 and the 3 here while you have a u in the problem, you're going to lose points on the AP exam. And that's because 1 and 3 are x values, all right? See the x right here? These are values of x. Once you put the u in, you either need to switch these to values of u, like I did in the previous method, or leave them out completely, like I just showed you just now. Number 6, a table of values for a continuous function f is shown. If 4 equal subintervals of 0 to 2 are used, which of the following is a trapezoidal approximation of the integral of f from 0 to 2? Here's a model to help you visualize what we are doing. This is trapezoidal approximation. So picture a trapezoid that's turned on its side. This is base 1, and this is base 2. We know that the area of a trapezoid is 1/2 base 1 plus base 2 times height. The height of a trapezoid is the distance between the bases. So this is the height right here. We are going to find the area of 4 trapezoids using 4 equal subintervals between 0 and 2. So the subintervals will be from 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. Let's fill in the base 1 and base 2 for each trapezoid. So if we were looking at the interval from 0 to 0.5, then base 1 is going to be the value of the function at 0. So base 1 will be 3. Base 2 is going to be the value of the function at 0.5. So that's also 3. So we have 3 and 3. Moving on to the second trapezoid. Moving on to the second interval, base 1 will be the value of the function at 0.5. That's 3. Base 2 will be the value of the function at 1.0, and that is 5. In a similar way, we will know that base 2 for the third trapezoid will be the value of the function at 1, which is 5. Base 2 will be the value of the function at 1.5, which is 8. Fourth trapezoid, base 1 will be the value of the function at 1.5, which is 8. And base 2 will be the value of the function at 2.0, which is 13. What about the height of each trapezoid? Well, remember that the height of a trapezoid is the distance between the bases. So that's just going to be the width of each interval. And we chose 4 subintervals of equal width. Each subinterval has a width of 0.5. So that means that the height of each trapezoid is going to be 0.5. The trapezoidal approximation of this integral will be the sum of the areas of these 4 trapezoids. So remember, the area of a trapezoid is 1/2 base 1 plus base 2 times height. So we have the 1/2 base 1 plus base 2, so that's 6, times the height of 0.5. And then for the second trapezoid, 1/2 base 1 plus base 2 is 8, height is 0.5. Third trapezoid, 1/2 base 1 plus base 2 is 13, times a height of 0.5. And the fourth trapezoid, 1/2 base 1 plus base 2, so that's 21, times the height of 0.5. If you need to evaluate this without a calculator, you might want to factor out the GCF. So 0.5 is the same as 1/2. And then we have a 1/2 in the front. So 1/2 times 1/2 is 1/4. So notice that each one of these terms has the 1/2 times 1/2 in it. So each term has 1/4. If we take that 1/4 outside of parentheses as a GCF, that's just going to leave 1/4 times 6 plus 8 plus 13 plus 21. So doesn't this seem simpler? These numbers add up to 48. So we have 1/4 of 48, which is 12. So the answer is B. Last problem. The acceleration alpha of a body moving in a straight line is given in terms of t by alpha equals 8 minus 6t. If the velocity of the body is 25 at time t equals 1, and if s of t is the distance of the body from the origin at time t, then what is s at 4 minus s at 2? Here are some notes that you need in order to solve this problem. Write this down. The change in position from A to B is always equal to the integral of the velocity from A to B. When they ask us to find s at 4 minus s at 2, understand this is the change in position from 2 to 4. So ultimately, the change in position from 2 to 4 will equal the integral of velocity from 2 to 4. So this is what we need to find. But we do not have a velocity equation, we have an acceleration equation. So how do we turn an acceleration equation into a velocity equation? You take the integral, of course. Here is the acceleration equation that they gave us. The velocity is going to be the integral of the acceleration. In other words, velocity will equal the integral of 8 minus 6t dt. So if you integrate 8, that's going to give you 8t. Using the power rule of integration, we will increase this exponent by 1 and make it t squared. Then we divide by the new exponent, and negative 6 divided by 2 is negative 3. Don't forget the constant of integration, c. They gave us enough information to find c. They told us that the velocity is 25 at time t equals 1. So in other words, the velocity at 1 is equal to 25. Substituting 1 for t in the equation for velocity, we have 8 times 1 minus 3 times 1 squared plus c is equal to 25. So this becomes 8 minus 3 plus c is equal to 25. So 5 plus c is equal to 25. Subtracting 5 from both sides, we have c is equal to 20. So let's make that substitution. So we have this equation for the velocity at t. Now we just need to find the integral of the velocity from 2 to 4, and that will be the change in position from 2 to 4. Let's evaluate this integral term by term. Increasing the power by 1, we have t squared. Dividing 8 by the new exponent gives us 4. Increasing this exponent by 1, we have t cubed. Dividing by our new exponent, we have negative 1. And then 20 will become 20t. Plus, well, I started to say plus c, but no. This is a definite integral, so we just need to evaluate using the limits of integration from 2 to 4. So we will find the value at 4 and then subtract the value at 2. So far we have this, which simplifies down to this, which simplifies to this, which equals 32. So the answer is D. At the beginning of this problem, I told you that the key was the change in position from A to B is equal to the integral of velocity from A to B. That is a very important concept. The only problem is I just realized that I haven't taught you that concept yet. So I'm not meaning to spring on you a brand new concept. We're going to learn this in Unit 7. So I'm going to go back and modify my solution a little bit to avoid having to use this concept. The first half of the problem will stay the same. We use the acceleration formula they gave us in order to find the velocity equation. We have learned that the position function will be the integral of the velocity function. So we will integrate the velocity function just like we did before, except this time it is an indefinite integral. There are no limits of integration. For that reason, we need to include a constant of integration, which I will call d this time because we used c earlier in the problem. We don't have enough information to find the value of d, but that turns out to be okay. The question is asking us to find s at 4 minus s at 2, and we can do that. So this is s at 4 minus s at 2. This should be looking really familiar compared to what we saw the last time, but this time we have a plus d here and a plus d here. So we simplify, and we simplify some more. We still have this d, but that's okay because once we distribute the minus sign, we have 80 plus d minus 48 minus d. So you can see that the plus d and the minus d will cancel each other out, and we are left with 80 minus 48, just like we had by the other method. So the answer is D.